See another example of solving a system of linear differential equations. We've written the system out in our linear algebra form again, and I've gone ahead and written down the eigenvalues and eigenvectors. There is only one eigenvalue, it's repeated, lambda equals 2, and this is the corresponding eigenvector. So we know that eigenvector e to the eigenvalue t is a solution. So we have a solution of our system, but for the general solution, we need another linearly independent solution, and we don't have that. And in the past, we got there through adding a t. And adding a t doesn't quite work here. What we need now is the generalized eigenvector. And the equation for the generalized eigenvector is a minus lambda I times eta equals v. All right, what does that mean? We have the a minus lambda I, so that's 1 minus 2, comma, negative 1, 1, and then 3 minus 2. That's a minus lambda I with lambda equals 2. Our generalized eigenvector we call eta, so eta 1 and eta 2. And then on the right-hand side is the eigenvector. Instead of a 0, it's 1 minus 1. It's the eigenvector. So we have here, right, the 2, that's the lambda. This is the eigenvector v. But this is once again a system of equations and unknowns. This looks like negative 1, 1, 1, eta 1, eta 2 equals 1, negative 1. We once again have two redundant equations, just like we did when we were finding eigenvectors. For the generalized eigenvector, we have redundant equations again, and the equation we have is negative eta 1 minus eta 2 equals 1. So this is our equation to find the eta 1 and the eta 2. Because there's only one equation for two unknowns, we once again have infinitely many possible solutions. We just have to pick one. So I am going to pick, I can pick eta 1 equals 0. And if I pick eta 1 equals 0, I get eta 2 equals negative 1. I can do that with the generalized eigenvalue because the right-hand sides are not 0. When I find the eigenvector, if I try to pick a 0 for v1, I'm going to get a 0 for v2, and I can't have a 0 eigenvector. But here, where the right-hand side is non-zero, I can pick a 0 and end up with a non-zero generalized eigenvector. So I have my generalized eigenvector, eta is 0, negative 1. I now have everything I need to put together the general solution. And the general solution is, cleaning solution there, sorry. The general solution is C1 times 1 minus 1 e to the 2t. That's just this. That's the first of my two linearly independent solutions. That's the eigenvector e to the eigenvalue t that I expected to have as a solution. Plus C2 times negative 1 t e to the 2t. So there's the extra t. It does show up. It is part of this solution. This is the same eigenvector e to the eigenvalue t, but there's an extra t in there. It's just that that's not quite enough to make this a solution. To make it a solution, I also need the generalized eigenvector 0 minus 1 times e to the 2t. So this is the general solution. It's the eigenvector e to the eigenvalue t, and then the eigenvector e to the eigenvalue t with the extra t, and then this bit with the generalized eigenvector and e to the 2t. Now, there are, in eigenvectors and generalized eigenvectors, there are choices we can make. I could have picked eta 2 equals 0, and then eta 1 would have been a negative 1, and this would look different. How can they both be solutions? When you plug in the initial conditions and get C1 and C2, it takes care of all of that, and we all get the same thing in the end, regardless of what we chose for our generalized eigenvector, or even our eigenvector, right? I could have had 2, negative 2 for the eigenvector. That would have been okay. It all gets fixed when you plug in the initial conditions. The C1 and C2s take care of all that, and we all end up with the same answer in the end, which is great when it comes to grading. Otherwise, it would be a nightmare. So